Hey everyone, me again, looking to talk to somebody about math. Are you interested? Today we're going to talk about the square root of a function. Now the square root of a function is another sort of transformation. We've talked about, translations, and we've talked about reflections, and we've talked about stretches. And all of those are different transformations that we could perform on a function. Taking the square root of an entire function is another type of transformation, okay? And it lends itself well in the middle of us talking about rationals and radicals because a radical is sort of like a square root, right? So you're gonna see some similarities in what happens and the shape of at least particular spots of the graph, okay? So, after working with the basics of radical functions in our previous lesson, we must now learn how taking the square root will affect an already given function. Our graphing calculator will be a very limited use here, okay? So we're gonna use our heads. So here's what we're gonna do. We're gonna consider the function y equals negative x plus 4. Without your graphing calculator, complete the table. Now, first of all, you should be comfortable to know that this is the graph of y equals negative x plus 4. I have a y-intercept at 4. I have a slope of -1. So from 4 on the y-axis, I'm going down 1, right 1, down 1, right 1. Okay. And so then what we've done is I've generated a table of values already for the original function. So when x is 0, y is 4. When x is 2, y is 2. When x is 2.5, y is 1.5. And so I've generated those points for you already. What I want you to do is generate the points for the square root graph. Now, the square root graph, essentially you're square rooting the entire function, right? But the entire function is really representative of the y values, right? We're always looking at the output when we're looking at a function. So when we square root a function, what we're doing is we're square rooting all the y values. So the x values are going to stay the same. The y values are going to get square rooted. So for instance, here in the original guy, you've got x is 0 and y is 4. So in the new guy, you're going to have x is 0, but now y will be 2 because we square root the 4. Okay, so pause me for a sec, fill in that table. Okay, welcome back, and this is what you should have. You should have 2, around 1.5, around 1.2, around 1, around 0.7, 0, and then for the negatives, you don't exist because you can't take the square root of a negative number, okay? All right, so now what I want you to do is I want you to try and plot that on top of the graph you already have there. You have y equals negative x plus 4. On top of that, we want to plot these new points. So we're going to plot 0, 2, 2, 1.5, 2.5, 1.2, and so on. Okay, go ahead and do that. Okay, and so you should have a graph that looks like this. Okay, and there are essentially 3 different regions that I want to talk to you about right away. I want to talk to you about when the graph is below, when the original graph, so that's my blue graph here, is below the x-axis, all the values would be, for y, would be negative there, right? All of my outputs for this function would be negative after x equals 4 there, right? Okay, what I want you to notice is in the square root graph, which is the red graph, nothing happens. The square root graph doesn't exist. And the square root graph doesn't exist because I'm trying to take a square root of a negative number and I can't do that. That doesn't happen. Okay. Then I want you to notice that at y equals 0, I have an invariant point. Okay. So at y equals 0, the new function is also 0, and that's because the square root of 0 is 0. I also want you to notice that at y equals 1, which is right here, if you can see my mouse circling, okay, y equals 1, that also doesn't change. So that again is an invariant point. And again, that's because the square root of 1 is 1, okay? So I actually have 2 invariant points in this graph, and those 2 invariant points break things up, as far as the range is concerned, into 3 different sections. One I've already talked about, and that's when I'm below 0 as far as the y values go. When I'm below 0, the square root graph doesn't exist. The next section is in between those invariant points. And so that's when y is between 0 and 1. okay? Take a look at that. When y is between 0 and 1, actually, what I want you to notice there is the red graph is riding just a little higher than the blue graph. The red graph is greater values, has greater values. That was bad grammar. The red graph has greater values than the blue graph does. That's because in between 0 and 1, that means all the y values are a fraction, right? When I square root a fraction, I actually get a number that's larger than the original number that I started with. Think about 1/4. When I square root 1/4, I get 1/2. 1/2 is larger than 1/4. So now, I don't know if you've caught on to what I'm doing here yet, but I'm taking this first example and I'm really just teaching you the whole entire note right now. This is how we're going to draw every square root graph if you understand these three little sections, okay? So in between y equals 0 and y equals 1, my square root graph always should be riding just slightly higher than the original graph. After that, we're looking at y is greater than 1. And so any value greater than 1, when I take the square root of it, I will get a number that's less than what I started with. And so that's why after that y equals 1 mark, which is right about here, you see that the red graph is always below the blue graph. So the values of my output on the red graph will always be lower than the values of my output on the blue graph, the original graph, when y is greater than 1. Okay, so 3 sections I want you to keep in mind, and we're going to write all this down as we go, okay? So if you're a little overwhelmed right now, if you're like, holy smokes, this is a lot to take in, it's okay. We're going to keep going with it, and you're going to see this over and over and over again. But I'm just trying to paint the bigger picture for you right away so that you can kind of come on this journey with me. So 3 regions. You're going to all, like, here's the point. You don't want to sit here and try and map out every square root of y on that blue line, right? If we could make this quicker and more efficient and still have a very accurate graph, that's what we want to do. And so that's where I'm taking you, okay? So you always want to plot your invariant points and your friendly points. So your invariant points are at y equals 0, that stays the same. Y equals 1, that stays the same. And now I said friendly points, and that's the first time I've said that. Friendly points are the ones that you know the square root of, right? You know that wherever the graph is on y equals 4, that's going to drop to 2 because you know the square root of 4 is 2. And sometimes you'll have a 9 in there as well, just depending on how big your graph is. So anywhere where you see a 9, y equals 9, that will drop to 3 because you know the square root of 9 is 3. Okay, once you have those dots, then you need to think about the 3 regions that I've described there. Okay, so when I'm below the x-axis, when y is less than 0, nothing happens, nothing exists. When I'm in between y equals 0 and y equals 1, the square root graph should be riding just a little higher than the original graph. And then after y equals 1, and your dots should help you with this, but like the friendly dots, after y equals 1, the square root graph should always be lower than the original function. Okay. All right. So now we're just going to write down everything I just said. Okay. So if you felt that that last 30 seconds went way too fast for you, you got time now. Also, don't forget you're watching this on YouTube, so you have the ability to shut me up and rewind me at any point. Okay. So don't stress. If you need to, go back 30 seconds, listen to my spiel again, and then come back and we'll write this stuff down. Okay, so are there any invariant points for the 2 functions? If so, where? And we've talked about that. That was at y equals 0 and y equals 1. So the invariant points are 4, 0 and 3, 1. Invariant points will occur when y equals 0 because the square root of 0 is 0, and where y equals 1 because the square root of 1 is 1. Okay. What do you notice about the x-intercepts of both graphs? Well, your answer there is they're the same. Will this always be so? Absolutely, it will always be so, because an x-intercept has a y value of 0, and that's an invariant point. Okay, so the x-intercepts are the same. They are both at 4, 0. This will always be the case as y equals 0 is an invariant point. I want you to take note the way I'm answering these questions. This is the way you would want to clearly communicate in a written response question for your diploma, okay? So I'm speaking in complete sentences, but I'm also giving information as I go. I'm not just saying that the x-intercepts are the same. I state what those x-intercepts are, okay? Your communication is a super, super important point of Math 30-1. Of math altogether, but I mean, I know you're focused on Math 30-1 right now, so let's stick with Math 30-1. Okay, now, when is the original graph, the graph of y equals negative x plus 4, above the square root graph? When is the original graph higher than the square root graph? That would be when y is greater than 1. Okay, so when the values, for the values where y is greater than 1, this is because the square root of a number larger than 1 will be smaller than the original number. Okay, when is the graph of y equals negative x plus 4, so the original graph, below the square root graph? Well, that's that moment between y is 0 and y is 1, okay? And our explanation there, again, is because I'm taking the square root of a fraction, and the square root of a fraction will be higher than the original number. So for values where 0 is less than y is less than 1, this is because the square root of a fraction will be larger. Now, notice I didn't say equal to there. I didn't say 0 is less than or equal to y, because at 0 and 1, they're on top of each other. They're invariant points, okay? Okay, and then what happens to the y values when x is what happens to the y values of the square root graph when x is greater than 4? At that moment, the y values of the original graph are negative, and I can't take the square root of a negative number, so the y values of the square root graph are non-existent. Okay, so when x is greater than 4, the square root graph does not exist. This is because the function is only defined when x is greater than 4. Think about the restrictions, right? If you go back to that radical conversation that we had 2 lessons ago, I think, the radicand has to be greater than 0. So we would say negative x plus 4 has to be greater than 0, and then we bring our 4 over. So negative x has to be greater than negative 4, and then we divide everything by negative 1, and that gives us x is less than 4. Okay, so the domain of this graph has to be x is less than 4. So if we looked at the original function, the values for y are negative when x is greater than 4, and you can't take the square root of a negative number. Okay. All right, so now we're going to do it again. I've just given you a different line. But think about everything that I just said, okay? I know I've said a lot. I'm going to go right away, and I'm going to plot my invariant point. So I got y equals 0, I got y equals 1. I'm going to plot my friendly numbers, so I know that the 4 right there will drop down to 2. Okay, and then I can use those dots. I can see the shape already. I know between here and here, I have to ride just a little above, and then I know that I have to hit that point, and from there on in, I kind of have a trajectory there that I can follow, okay? So this is what the graph should look like, okay? Now, the domain, the range, the invariant points, we're gonna fill in the table. I guess it's directly below me right now. My big old head might be in the way. Let me just take my head off for a sec, just so you can see the full table, if you need to see the full table. Okay, so the domain is going to be x is greater than 1. The range will be y is greater than 0. The invariant points, I have 2 of them in this case. One was at 1, 0, and the other was at 1.5, 1. Okay, I did not give you an equation to this graph. If I gave you the equation to this graph for the invariant points, I would expect that you algebraically plug in 0 for y and solve for x, and then algebraically plug in 1 for y and solve for x. Okay, in this one right now, we're just getting warmed up and we're just estimating based on the graph that we drew. Okay, I know I have an x-intercept at 1, 0. There is no y-intercept. The region when the original is greater than the square root graph is when x is greater than 1.5. And then the region where the original is underneath the square root graph, that would be between 1 and 1.5. So I said 1 is less than x is less than 1.5. Okay. Awesome. Okay, try this guy. I'll get that ink out of the way for you there. Again, we don't have to do every point. What we have to do is we have to plot our invariant points, plot our friendly points, and then think about how these things fit together. So my invariant points are going to be at 0 and at 1, y equals 0, y equals 1. My friendly points, I've got a y equals 4 there, so I'll drop that down to 2. And so I've done that, and then I can easily connect those dots following the pattern. I know that between y is 0 and y is 1, I have to be above, and then after y is 1, I have to be below, and below the x-axis, I don't exist. Okay, so now the domain of this guy will be x is less than 0. The range will be y is greater than or equal to 0. I should have said equal to on the domain as well, sorry. Invariant points will be at 0, 0, and -1, -1. X-intercepts will be at 0, 0. Y-intercept is also at 0, 0. The region where the original is greater is when x is less than -1. And then the region where the original is less than the square root graph, that would be between -1 and 0. So -1 less than x less than 0. Okay. I'm hoping now it's starting to solidify all that stuff I said at the beginning. As we go through examples, I'm hoping you're starting to feel a little better about it. So we've dealt with linear ones. Now we want to take a look at quadratic ones when I take the square root of a quadratic function. Okay. Okay. We'll just answer these questions first. What do you know about the graph of y equals the root of f of x at f of x equals 0 and at f of x equals 1? Well, I know I have invariant points there. Okay, and sorry, can't talk. How do the graphs of y equals f of x and y equals the root of f of x compare on either side of the locations from the previous question? Again, those are these three little points of the range that I want to talk about. So when y is less than 0, the square root graph doesn't exist. When y is between 0 and 1, the square root graph will be above the original, or the original will be below the square root graph, however you want to look at that. And when y is greater than 1, the square root graph will be below the original, or the original will be above the square root graph. Okay? Awesome, possum. Okay, so now we are going to do quadratics like I promised. Okay, first thing we're going to do is plot those invariant points, just like I did with linear. Okay, nothing's changed. So I've got y equals 0 and I've got y equals 1. Well, a few things have changed. I have more invariant points than what I did with linear, right? Now I want you to look at this and say, hey, I have 4 different invariant points because I have 2 at y equals 0, here and here, and I have 2 at y equals 1, here and here. Okay. Okay, now this provides a very, we should plot our friendly points too. Hey, that would be good. So at 4, then I'll get into my interesting talk. At 4, I drop down to 2. So I'm just going to put a point there. And at 4, I drop down to 2. So I'm just going to put a little friendly point there. Okay. In between -2 and 2, the y values of the original graph are negative, which means the square root graph doesn't exist. So I'm wondering if you can visualize this already, that this is what we would call a two-tailed graph. It's going to go like this with nothing in the middle. Okay, so it looks like this. Okay, there's nothing in the middle. And so I have this portion here that would be less than -2, and I have this portion here that would be greater than +2. Okay, so that is my domain. My domain is all the values of x such that x is less than -2, less than or equal to -2, sorry, and x is greater than or equal to +2. My range is still y is greater than or equal to 0. I have 4 invariant points. I've got it at, again, I'm just kind of guessing right now, but I would say that's maybe -2.3, -2.4, comma 1, -2, comma 0, 2, comma 0, and 2.3 maybe, 2.2. What did I say? I said 2.1. Yeah, I guess since that's all the way to 3, 2.1, 2.2, I'd take either one of those. 2.3, 2.4 was probably going a little too far to the center there. Okay. So I said negative 2.1, comma 1, negative 2, comma 0, 2, comma 0, and 2.1, comma 1. My x-intercepts, I have 2 of them at negative 2, comma 0, and 2, comma 0. Y-intercepts, I don't have any. The minimum value here is y equals 0, and the maximum value is none. There is no maximum value. Now be careful with this. I need the word none here. Don't put 0 because 0 is a number. If you put 0, I'm going to think maybe you think there is a maximum value and maybe you think it's at 0. Okay? Physically write the word none. Don't put nothing there, okay? Because then I think you just skip the question because you don't know what you're doing, okay? Don't put a slash through it because then I think you're just stressed about that question and you want to avoid it. Write the word none. There is no maximum value there, okay? Oh, another little conversation there is be careful, don't put infinity, okay? Some kids think, oh, I'm going to look really, really smart and I'm going to say the maximum value is infinity. That's kind of a misnomer because infinity isn't a value, it's a direction. So if I ask you for the value, infinity is not an answer that you can give me. You'd have to say there is no maximum value, okay? All right, let's try this guy. I'll get my ink off from the previous question there. So again, I'm gonna plot my friendly things. I've got y equals 0, we'll stay at 0. Y equals 1, we'll stay at 1. Y equals 4, we'll drop down to 2. That's all of those points. 4 of them are invariant and 1 of them was friendly. Now, I'm just going to connect all those dots. I have to remember, though, that between here and here, I need to be writing just above what the original graph was. Also, between here and here, I need to be writing just above. And so that's going to look something like that. Okay. So my domain this time will be between 0 and 4. So all the values of x such that 0 is less than or equal to x is less than or equal to 4, where x is a member of the reals. My range will be from 0 to 2. I have 4 invariant points again. So do you like that? I said 4 invariant points. My range will be between 0 and 2. I said that. Okay, my invariant points will then be 0, 0, 0.3, comma 1. Again, I'm guessing a little bit there. 3.7, comma 1, and 4, comma 0. I'll have x-intercepts at 0, 0, and 4, 0. Y-intercepts at 0, 0. This time I do have a minimum and a maximum value. My minimum value is at y equals 0. My maximum value is at y equals 2. Max and mins are always just the y value. They're not the coordinate point. They're the y value, okay? All right, use the following graph of y equals f of x to answer the questions below. Determine the domain of y equals f of x. Well, I'm gonna end up going, this is going to be a two-tailed graph. Hopefully you can see that. And so I'm going to be less than a and I'm going to be greater than b for my domain. Okay, so the domain, all the values of x such that x is less than or equal to a, x is greater than or equal to b, and x is a member of the reals. Determine the number of invariant points on y equals f of x. Well, I'd have 4 and they would be at a, b, c, and d. And then label where the original graph is less than the square root graph. Well, that would be from C to A and from B to D. Okay, so between C and A and between B and D. Okay, cool. All right, so we'll summarize this. The key values to consider when looking at y equals the root of f of x would be at y equals 0 and y equals 1, because those are my invariant points. The domain for the square root graph consists of all values in the domain of the original for where f of x is greater than or equal to 0. Okay, because if the original was less than 0, I can't take the square root of a negative number, and so my graph in this, or my graph in the square root graph doesn't exist. Okay, no values would exist where the original was negative because I can't take the square root of a negative number. The range of y equals the square root graph will consist of the square roots of all the values of the original for where the square root is defined. That's another way of saying 0.2 really. Okay. Okay, The y coordinates of the points on the graph of y equals the root of f of x are the square roots of the original y values. Okay, so essentially I take all the y values of my original function, I square root them, and that's my new y values. The x values stay the same. That's my new y values for the square root function. Okay. All right, so that's where we'll stop for this lesson. I've given you your homework there, and if you have any questions, pop in and see me, email me, connect with me somehow. I'm around. I'm not far away. Okay, have a great day, guys.